Our entire universe was once smaller than a single atom. In that first fleeting fraction of a second, an event called cosmic inflation stretched the fabric of reality itself, and microscopic quantum jitters were blown up to become the blueprint for everything. By the end of this journey, you will understand how the grand cosmic web of galaxies was born from subatomic randomness. How did a uniform burst of energy create the intricate structure we see today? And what does it mean that our existence hinges on quantum dice rolls from the dawn of time? What does it feel like to trace your origins back to the very first instant of everything? The universe was a realm of pure energy, a searing ocean where the fundamental forces we know today were indistinguishable. At this unimaginable moment, gravity was not yet a gentle curve in spacetime, and light did not yet travel freely. Everything was merged into a single, unified superforce, a state of such extreme simplicity and energy that our current laws of physics simply break down trying to describe it. This is the starting point, the blank canvas upon which our cosmic story begins. Yet, for decades, this picture created profound puzzles for cosmologists. The first was called the horizon problem. If you look at the most distant, ancient parts of the universe in opposite directions, the cosmic microwave background radiation they emit is almost exactly the same temperature. But according to the standard Big Bang timeline, those regions were never close enough to exchange heat or information. They were like two strangers on opposite sides of an ocean who, without ever meeting, decided to wear identical outfits. How could they possibly have coordinated that? The second major puzzle was the flatness problem. Our universe appears to be geometrically flat on the largest scales, a delicate balance between the energy of expansion and the pull of gravity. For it to be this flat today, its initial conditions had to be fine-tuned to an absurdly precise degree, like balancing a pencil on its tip for billions of years. These were not minor quirks. They were glaring signs that our understanding of the universe's first moments was missing a crucial chapter, a mechanism that could smooth out these contradictions and set the stage for everything to come. Into this cosmic standoff stepped a young physicist named Alan Guth. He wasn't initially trying to solve the universe's biggest mysteries. He was working on problems in particle physics in 1979. Wrestling with the behavior of exotic states of matter predicted by grand unified theories. But as he pieced together the equations, something astonishing clicked. Guth realized that a particular high-energy state, which he called a false vacuum, could possess a bizarre property. It would generate a powerful, repulsive gravitational force. This wasn't a force pushing things apart within space. It was a property that would cause the fabric of space itself to stretch, and to do so at a rate far exceeding the speed of light. In a flash of insight, he saw this as the missing chapter. He scribbled in his notebook a now famous phrase, calling it a spectacular realization. This was the birth of the inflationary hypothesis. The idea was both radical and elegantly simple. For a fleeting instant, perhaps around 10 to the negative 36 seconds after the beginning, a patch of the primordial universe became trapped in this false vacuum state. Think of it like a ball perched at the very top of a hill in a state of unstable, high-energy potential. While in that state, the repulsive gravity took over. Space didn't just expand, it inflated exponentially, doubling in size over and over again in intervals so brief they defy comprehension. In a time span shorter than a trillionth of a trillionth of a trillionth of a second, a subatomic speck of reality was blown up to a size larger than our entire observable universe today. That number is staggering. The expansion factor was at least 10 to the power of 26. To put that in perspective, if an atom were inflated by that same amount, it would become larger than a galaxy. This incredible burst of stretching was the key that unlocked the cosmic puzzles. The horizon problem vanished because everything we see in opposite directions was once intimately connected in that tiny, pre-inflationary patch, thoroughly mixed and smoothed to a uniform temperature before being flung apart. The flatness problem was solved because inflation acted like a cosmic iron, stretching any initial curvature so immensely that the resulting universe appears perfectly flat to us, just as the surface of a giant balloon feels flat to a tiny ant crawling on it. Guth's bold idea didn't just fix the old problems, it set the stage for the universe's most important creative act, transforming the featureless into the structured. For when inflation ended, that false vacuum energy decayed, releasing a firestorm of particles and radiation, essentially resetting the hot Big Bang. But what was left imprinted on this newly energized cosmos? The answer lies in the quantum world, and it would give our smooth, inflated universe its first crucial imperfections. But what could possibly generate such a titanic force, a pressure so immense it could stretch reality itself faster than light? The answer lies not in any particle or substance we know, but in a hypothetical energy field that may have saturated the infant cosmos. Physicists call it the Inflaton field, a kind of cosmic engine that was stuck in the wrong gear. To understand its power, we need to grasp a strange concept known as the false vacuum. Picture a landscape of energy states. The lowest point, the true vacuum, is like a peaceful valley where the universe naturally wants to settle. But in its earliest moments, the Inflaton field found itself trapped on a high plateau, a state of unstable but incredibly dense energy. This is the false vacuum. The bizarre property of this state is that its energy density doesn't dilute as space expands. Think of a stretched balloon. Normally, the air inside becomes less dense as the rubber stretches, but in this false vacuum, the energy density remains constant. It's as if new energy is constantly being created to fill the newly created volume, and that energy itself generates more repulsive gravity, which creates more space in a runaway, exponential feedback loop. This is the relentless engine that powered inflation. The field was like a ball perched precariously on that high plateau, yearning to roll down into the valley of the true vacuum where it could relax. But for that brief, critical instant, it was held in place, and as long as it remained there, space continued to inflate at a staggering rate, smoothing and stretching the universe to cosmic proportions. This unstable configuration couldn't last forever. Eventually, through quantum processes, the Inflaton field began to decay. Like water finding a crack in a dam, it started to tumble down from its high-energy plateau. And when it finally reached the true vacuum, that immense store of false vacuum energy was released in a cataclysmic flash. This was not an explosion in space, but the conversion of the field's potential energy into the raw ingredients of our universe. That released energy reheated the cosmos, flooding it with particles and radiation, effectively resetting the hot, dense conditions we traditionally call the Big Bang. So inflation didn't replace the Big Bang. It was the spectacular opening act that set the stage for it, but the story doesn't end with a smooth, reheated cosmos. The most profound legacy of inflation was written in the final moments of its decay, etched into the universe by the faintest whispers of the quantum world. This single, breathtaking event of inflation didn't just create space, it solved two of cosmology's deepest mysteries in one elegant stroke. Take the horizon problem, the puzzle of the universe's identical temperature in opposite directions. The classic Big Bang timeline left these regions forever isolated, like distant islands that somehow grew the same rare flower without any contact. Inflation rewrites that story completely. Before the great stretching, that tiny primordial patch was smaller than a single proton, and every part of it was in intimate causal contact. Heat and energy could flow freely, mixing everything into a perfectly smooth, uniform broth. Then inflation took over, stretching that smoothness to cosmic scales, carrying those once connected regions to opposite ends of the observable universe. They look disconnected now, but their matching temperatures are simply a fossil, a memory of their shared origin in that tiny, pre-inflationary neighborhood. The flatness problem meets a similar fate. For the universe to appear as geometrically flat as it does today, its initial curvature had to be fine-tuned to an almost impossible precision. Inflation provides a natural, mechanical explanation. Imagine you are an ant living on the surface of a giant, wrinkled balloon. From your tiny perspective, the surface looks wildly curved and contorted. Now, someone begins to inflate the balloon to an immense size. As it stretches, the wrinkles smooth out, and the small patch of rubber you stand on becomes flatter and flatter. Inflation did exactly this to the fabric of spacetime itself. Any initial curvature, no matter how pronounced, was stretched so immensely by that exponential expansion that the resulting universe appears perfectly flat to us, just like the vast ocean appears flat to a sailor on its surface. This isn't a coincidence or a delicate setup, it's the inevitable outcome of that colossal stretching. So inflation delivers a universe that is both remarkably smooth and geometrically flat, not because of magical initial conditions, but as a direct consequence of its own explosive growth. Yet, if inflation only created perfect smoothness, we would have a profound new problem. A perfectly uniform universe would have remained a featureless sea of particles, with no galaxies, stars, or planets. The true magic of inflation is that it didn't create a flawless canvas. It created a canvas with the most subtle, crucial imperfections imaginable, the seeds from which all cosmic structure would eventually grow. But perfect smoothness is a dead end for a creative cosmos. For galaxies to form, the universe needed seeds, tiny pockets where gravity could eventually get a foothold. And remarkably, inflation didn't just erase imperfections, it generated them from the deepest laws of physics. The source was the quantum nature of reality itself. In the realm of the very small, nothing is ever still or certain. Even in what we call empty space, there is a fundamental fuzziness, a ceaseless bubbling of virtual particles popping in and out of existence. These are quantum fluctuations, momentary borrowings of energy from the vacuum, permitted by the uncertainty principle. They are the universe's subatomic static. During inflation, the Inflaton field was not immune to this quantum jitter. Its value at any given point wasn't a fixed number, it was a probability. Think of it like the surface of a pond on a windy day. Even as a steady breeze creates large, smooth waves, the surface is also covered in a fine, random texture of tiny ripples from countless minute disturbances. Those tiny ripples are the quantum fluctuations in the field. In the ordinary, slow-moving universe, these fluctuations are fleeting and microscopic, vanishing almost as soon as they appear. But inflation changed the rules completely. As space expanded faster than light, these infinitesimal quantum ripples were caught in the act and stretched to astronomical sizes. A fluctuation that spanned a quantum scale one moment could, in the next unimaginably brief instant, be inflated to a scale larger than a galaxy. The process was like taking a fingerprint from a single cell and blowing it up to cover an entire continent. Crucially, these ripples didn't get smoothed out. They were frozen into the very geometry of the expanding universe as inflation ended. Where the Inflaton field had a slightly higher value due to a quantum jitter, the inflation process ended a tiny bit later, leaving behind a minute over density of energy. Where the field had a slightly lower value, inflation ended a touch earlier, resulting in a subtle underdensity. This created a pattern, a faint imprint of hills and valleys in the energy density of the hot plasma that filled the post-inflation cosmos. These were not yet structures, but the cosmic blueprint was now drawn. The universe was no longer perfectly smooth. It was imprinted with the amplified whispers of quantum static, the primordial seeds from which gravity would, over billions of years, sculpt every galaxy, star, and planet. The grand architecture of our cosmos began as subatomic noise, magnified to a cosmic scale by the most violent expansion imaginable. But how exactly does a fleeting quantum jitter become a permanent cosmic feature? The transformation hinges on two critical stages, stretching and freezing. First, consider the wavelength of a quantum fluctuation, the physical size of that tiny ripple in the Inflaton field. In the ordinary world, such a wavelength is vanishingly small. Yet as inflation accelerated, space itself was stretching at a rate that defied intuition, and the wavelength of the fluctuation stretched right along with it. This is the process physicists call horizon crossing. Imagine you are standing on a tiny raft in the middle of an ocean during a sudden, violent storm. At first, you are surrounded by choppy, close-packed waves, but then the ocean itself begins to expand at a fantastic speed. The distance between wave crests grows longer and longer. Very quickly, the wavelength of the waves around you becomes larger than the distance you can see in any direction. You are no longer in a local sea of choppy water. You are sitting on a single, vast, gentle swell that extends far beyond your horizon. This is what happened to every quantum ripple. As inflation blew up the universe, the wavelength of each fluctuation was stretched so immensely that it exceeded the cosmic horizon, the distance light could have traveled since the beginning. At that precise moment, something profound occurred. The fluctuation could no longer evolve or interact with itself. It was caught, fixed in place by the geometry of the expanding space. It became frozen in, a permanent undulation etched into the fabric of reality. We can think of it like drawing a tiny, intricate pattern on the surface of a balloon with a fine-tipped pen. If you then inflate the balloon to the size of a house, the pattern is still there, but now it is stretched into a large, faint, and permanent feature on the rubber. The rapid expansion locked the quantum pattern in place before it could fade away. These frozen imprints were not ripples of the Inflaton field anymore. They translated directly into tiny differences in the density of the universe. Where a frozen ripple represented a slightly higher energy, it left behind a region with a minute over density of matter and energy after reheating. Where it represented a lower energy, it left an under-density. The result was a cosmic canvas painted with the faintest of textures, a pattern of hills and valleys in the density of the primordial plasma. These are the primordial seeds, the universe's original blueprint. Those slightly denser patches, imperceptible at first, held an extraordinary future. They were the places where gravity would eventually gain a tiny advantage, slowly pulling in more and more matter over billions of years, leading to the first stars and galaxies. The slightly less dense regions would become the vast, empty cosmic voids we see between galactic filaments. So the grand cosmic web, with its brilliant nodes of light and its dark, empty expanses, is not random. It is the ghostly, amplified echo of quantum static from the universe's first moment, stretched to cosmic scales and frozen in time by inflation's incredible power. The most astonishing part is that inflation didn't just create random seeds, it left a specific, predictable signature. The quantum fluctuations imprinted on the cosmos weren't chaotic. They followed a precise statistical pattern, a kind of cosmic rulebook for how matter would eventually clump together. This pattern is known as the Harrison-Zel'dovich spectrum, named for the physicists who independently deduced its necessity. Their insight was profound. For gravity to build the structures we see, from the smallest galaxies to the largest superclusters, the initial seeds needed a very particular character. They needed to be nearly scale-invariant. Now, what does that mean? Think of it this way. If you look at the distribution of matter in the universe on the scale of a single galaxy, you see a certain level of lumpiness, a specific amplitude of the hills and valleys in the density. Scale invariance predicts that if you zoom out to the scale of a cluster of galaxies, or even to a vast filament spanning billions of light years, the relative level of lumpiness should be roughly the same. The fluctuations have no preferred scale. A useful analogy comes from sound. In audio engineering, white noise is a signal that contains equal power across all audible frequencies. From the deepest bass rumble to the highest treble chirp, the intensity is uniform. The scale-invariant spectrum of cosmic seeds is the spatial equivalent of this white noise. It contains equal gravitational potential or clumping strength across all cosmic distance scales. This is not what you would intuitively expect. Most physical processes favor one scale over another. A stone dropped in a pond creates ripples of a certain size dictated by the stone's weight and the water's tension. But the quantum fluctuations stretched by inflation remember no such origin. Their pattern reflects the uniform, exponential expansion itself, a process that treats all scales equally as it blows them up. This prediction became the ultimate litmus test for inflation. If the theory was correct, then the faint temperature variations in the cosmic microwave background, the afterglow of the Big Bang, should reveal this telltale scale-invariant pattern. It was a bold forecast, a cosmic fingerprint left in the cold light of creation, waiting to be discovered by our telescopes. For nearly 400,000 years, the universe remained a searing, opaque fog. Light could not travel freely as photons were constantly scattered by a thick plasma of charged particles. But then, as the cosmos expanded and cooled, a pivotal change occurred. Electrons and protons combined to form neutral hydrogen atoms, and suddenly the fog cleared. The light that had been trapped within that plasma was finally set free, streaming across space in every direction. That ancient light is what we detect today as the cosmic microwave background, and it carries with it a perfect snapshot of the universe at that moment of first transparency. This faint, cold glow is the oldest picture we have of everything, and etched into its subtle temperature variations is the very blueprint inflation left behind. The CBM is not perfectly uniform. When we map it across the sky with exquisitely sensitive instruments, it reveals a mottled pattern, like the texture of an orange peel or the gentle static on an old television screen. These tiny temperature differences are the key. A region of the sky that appears just a few millionths of a degree warmer than average corresponds directly to a region of the primordial plasma that was slightly denser. Why? Because gravity was already at work. In a slightly denser patch, photons had to climb out of a slightly deeper gravitational well as the universe became transparent, losing a tiny bit of energy in the process, which makes them appear ever so slightly cooler to us. Conversely, photons from an underdense region had an easier escape, arriving with a bit more energy, appearing as a slightly warmer spot. This intricate pattern of hot and cold is not random noise. It is the direct imprint, the frozen echo, of those quantum density seeds stretched across the sky. Confirming this prediction required a new generation of cosmic cartographers. The first to hear the whispers clearly was the Cosmic Background Explorer satellite, or COBE, launched in 1989. Its instruments were so sensitive they could detect temperature variations of about 1 part in 100,000. When the COBE team presented their first map in 1992, it sent a shockwave through cosmology. There, plain to see, was the primordial modeling. The universe's baby picture was not a smooth, featureless blank. It was textured with the seeds of all future structure. For this monumental discovery, the project's leaders were awarded the Nobel Prize in Physics. COBE had seen the forest. The next missions would map every tree. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, provided a far sharper image, measuring the CBM with breathtaking detail and allowing scientists to determine the universe's age, composition, and geometry with unprecedented accuracy. Then came the Planck satellite, a European Space Agency mission that operated from 2009 to 2013. Planck was the ultimate cosmic photographer. Its maps are so precise they reveal not just the temperature variations, but also the subtle polarization of this ancient light, a second layer of information imprinted by the very gravitational waves that may have rippled through spacetime during inflation. The pattern revealed by these missions matched the predictions of inflationary theory with stunning fidelity. The fluctuations were nearly scale-invariant, just as the theory demanded. The hills and valleys in the cosmic density field, born from quantum jitters, were now a visible, measurable fact. We were literally looking at the amplified quantum noise from the first moments of time, captured in the cold light of the universe's dawn. This map is more than a relic. It is the Rosetta Stone of cosmology, and its translation tells us that our entire cosmic history, from the first stars to the galaxy we call home, was written in a code of quantum randomness expanded to a universal scale. The cold light of the cosmic microwave background is a cosmic message in a bottle, but to read it, we needed to learn its language. Scientists don't just look at the mottled map and nod. They translate its patterns into a precise mathematical dialect, a tool called the power spectrum. Think of it like analyzing a complex piece of music. You could listen to a symphony and describe it as beautiful or chaotic, but a composer would break it down into a spectrum of notes, measuring the strength of each frequency, from the deep hum of the bass to the high trill of the violin. The power spectrum does this for the cosmos. It takes the map of hot and cold spots and measures how much clumping exists at different angular scales on the sky, from vast continent-sized patches down to finer, mountain-sized ripples. This breakdown reveals the hidden architecture of the primordial seeds, and what the data shows is a symphony that matches the inflationary score with remarkable precision. The fluctuations follow a nearly scale-invariant pattern, meaning the relative strength of the clumping is roughly the same whether you look at large scales or small ones. They are Gaussian, which is a statistical way of saying the distribution is random and balanced, like the outcome of rolling a perfectly fair die an infinite number of times. No single, weirdly hot or cold spot stands out as a special event. It's all consistent with the gentle, random jitter of quantum fields, and they are adiabatic, meaning the recipe for the universe. The ratio of ordinary matter to dark matter to radiation was the same everywhere, just stirred into slightly denser or thinner clumps. This is exactly what you'd expect if a single, smooth field, the Inflaton, underwent quantum ripples that were stretched across the cosmos. The power spectrum is more than a match, it's a precise fingerprint. The detailed shape of its curve, with a specific series of peaks and troughs, tells physicists not just that inflation happened, but details about the energy landscape the Inflaton field rolled down. It's like hearing the specific echo of that primordial event. Perhaps the most breathtaking number to come from this analysis concerns the geometry of space itself. The pattern of the spots, especially the apparent size of the largest fluctuations, acts as a cosmic ruler. Measurements from the Planck satellite show that the universe is geometrically flat to an astonishing precision of about 0.4%. This isn't just roughly flat, it is exquisitely, definitively flat on the largest scales. This single finding resolves the old flatness problem with overwhelming force. Inflation's exponential stretching didn't just make the universe large, it ironed out any initial curvature to a degree that leaves no room for doubt in our observations. The agreement between the inflationary prediction and the CMB data is not a vague suggestion, it is a pillar of modern cosmology. When a theory makes a bold forecast about the state of the universe some 13.8 billion years before we had the tools to check, and then our tools reveal a match of such stunning detail. We are witnessing the extraordinary power of the scientific method. The ancient light tells us that the quantum seeds of our existence were sown in a fleeting, violent burst of expansion, and that the blueprint for everything we see was frozen into the cosmos before the first star ever ignited. Yet the cosmic microwave background holds a second, even more elusive layer of information. Beyond its faint variations in temperature, this ancient light carries a subtle property called polarization. As the first atoms formed and photons began their long journey, the way they scattered off the final particles of the primordial plasma imprinted a specific orientation, a directional fingerprint onto the light itself. This polarization is a treasure map pointing to two different kinds of events in the early universe. The first, called E-mode polarization, has already been detected and beautifully confirms the story of density waves, the acoustic oscillations set in motion by those initial quantum seeds. But the second type is the true holy grail. It is known as B-mode polarization, and finding it would be a discovery of monumental proportions. B-mode polarization would not be created by simple density fluctuations in matter. Its signature requires something far more dramatic, a twisting or curling of spacetime itself. The only force in the infant cosmos powerful enough to create such a pattern would be primordial gravitational waves. These are not the gravitational waves we detect today from colliding black holes or neutron stars. Those are the recent chirps and rumbles of cosmic violence. Primordial gravitational waves would be something else entirely, the fossilized ripples in the very fabric of reality, generated by the violent tremors of cosmic inflation itself. If temperature maps show us the imprint of quantum jitters in the Inflaton field, then detecting these B-modes would be like hearing the echo of spacetime being stretched. It would be the direct soundtrack to the universe's explosive birth. The hunt for this faint signal is one of the most challenging endeavors in modern cosmology. The B-mode signal is incredibly weak, buried under foreground noise from our own galaxy's dust and other astrophysical effects. Leading this search are ambitious experiments like the BICEP and Keck array telescopes, stationed at the South Pole where the cold, dry, stable air offers a crystal-clear view of the cosmos. In 2014, the BICEP2 team announced a thrilling but ultimately premature detection that was later attributed to interstellar dust. This episode highlighted the immense difficulty of the task. It is a painstaking process of observation, data analysis, and ruling out every possible contaminant. The quest continues with ever more sensitive instruments. Future space telescopes, designed specifically to map the CMB's polarization with unprecedented precision, are on the drawing board. Their goal is to peer through the cosmic dust and see if the telltale swirls of B-mode polarization are truly there, etched into the first light. A definitive detection would be the smoking gun for inflation, providing direct evidence of the gravitational upheaval that accompanied the universe's first fraction of a second. Even the absence of a signal, if established with enough certainty, would force a profound rethink of how inflation unfolded. This search pushes our technology to its absolute limits, building detectors that can measure temperature variations of a few billionths of a degree. It is a testament to our desire to listen for the faintest whispers of creation, to move from seeing the blueprint of our cosmic home to hearing the very vibrations of its foundation. The universe's exponential growth could not continue forever. The Inflaton field, trapped in its high-energy state, was inherently unstable. Like a ball perched on the very peak of a hill, it only needed the slightest nudge to begin its descent. That nudge came from the quantum world itself. Through a process known as quantum tunneling or slow roll, the field began to decay from its false vacuum, cascading down the energy landscape toward its true, stable minimum. This moment of transition is what cosmologists call reheating, and it was the most transformative event since inflation began. As the Inflaton field rolled down, its immense potential energy, which had been driving the repulsive gravity of inflation, was suddenly released. This wasn't an explosion in space. It was the conversion of the field itself into a raging firestorm of fundamental particles and radiation. Picture a colossal dam holding back an entire ocean. For eons, the water is held in place, storing unimaginable potential energy. Then the dam crumbles. The water doesn't just trickle out, it erupts in a cataclysmic flood, filling the valley below with a churning, turbulent sea. Reheating was that flood for the cosmos. The cold, empty, but vastly stretched space left by inflation was instantaneously flooded with energy, repopulating the universe with a searing, dense plasma. This event marks the true beginning of what we traditionally call the hot Big Bang. All the energy for the particles, light, and heat that would fill the universe for billions of years came from this single release. The universe was reborn in fire, resetting the clock on a hot, dense state from which our standard models of cosmology can take over. In that first instant of reheating, the universe was a cauldron of pure energy, so intense that particles like quarks, leptons, and photons could not exist as distinct entities. They were constantly created and annihilated in a frenzied blur. But as this new, hot universe expanded and cooled, those energies dropped, allowing the first stable particles to condense out of the energetic soup. Quarks combined to form protons and neutrons. Electrons emerged. Photons, the particles of light, filled every corner, constantly bouncing off the charged plasma. This set the stage for the next great act, nucleosynthesis, where those protons and neutrons would fuse into the first atomic nuclei, the seeds of hydrogen and helium that would later fuel the first stars. So reheating is the essential bridge. It connects the mysterious, quantum-driven epoch of inflation to the familiar, particle-driven narrative of cosmic evolution. Without it, inflation would have left behind only a cold, empty, and sterile void. Instead, that violent release of energy gave us a universe brimming with potential, a canvas now painted with the quantum seeds of structure and flooded with the raw material to build upon them. The universe was now a canvas painted with faint ripples, a smooth sea of hot plasma marked by the slightest of hills and valleys. But a canvas is not a cathedral. For the grand architecture of the cosmos to rise, those subtle density differences needed an architect. That architect was gravity, and its work would be patient, relentless, and utterly transformative. With the primordial seeds frozen into the fabric of reality, gravity finally had something to grasp. Those regions of minute over density, imprinted by quantum jitters, held an invisible advantage. They contained just a little more mass than their surroundings. In the expanding universe, this was crucial. While the overall expansion of space works to pull everything apart, gravity is a local contractor, working within that expansion to pull things together. Think of it like a vast, rising loaf of raisin bread. As the dough expands, all the raisins move apart from one another. But if a few raisins were, by chance, clustered a bit closer together at the start, their own tiny mutual gravitational attraction can resist the stretching just a little bit more. They become a slightly stickier clump within the expanding loaf. For hundreds of millions of years, this was the silent drama playing out across the cosmos. But there was a hidden player making it all possible, an invisible scaffolding upon which the visible universe would be built. This was dark matter. We cannot see it directly, as it does not emit or absorb light, but its gravitational influence is undeniable. Dark matter, unaffected by the pressure of radiation that buffeted ordinary atoms, began to clump first. It flowed into the gravitational wells of those overdense seeds, creating dense, invisible halos. These dark matter halos became the gravitational skeletons for everything to come. They were the deep pits into which the ordinary atomic matter, the hydrogen and helium gas, could eventually flow. Once the universe had cooled and expanded enough, that gas, now free from the intense radiation pressure, felt the relentless pull of these dark matter concentrations. It cascaded into the halos, swirling and compressing, and in the densest, hottest cores of these collapsing clouds, a miracle of physics ignited. Nuclear fusion began. The first stars, monstrous and brilliant, burst into light, ending the cosmic dark ages and flooding the universe with new energy. These were not like the stars of today. They were behemoths, hundreds of times the mass of our Sun, living fast and dying in spectacular supernova explosions that seeded space with the heavier elements necessary for planets and life. But gravity's work was not done with individual stars or even isolated galaxies. The initial seed pattern was a cosmic interconnected tapestry. The slightly denser regions were not isolated dots. They were linked in a vast, three-dimensional network. As gravity continued its work over billions of years, it drew matter not into random islands but along these preordained lines. Galaxies formed, and they too felt the pull of the larger pattern. They began to stream along invisible filaments of dark matter, sliding toward the intersections where multiple filaments met. At these great cosmic crossroads, matter piled up into immense clusters containing thousands of galaxies, swimming in seas of superheated gas. The voids, the under-dense regions from the primordial blueprint, were left behind, growing ever emptier as matter drained toward the nodes and filaments. This is the cosmic web, the large-scale structure of the universe. It is a sponge-like architecture of brilliant filaments and dense clusters set against a backdrop of profound nothingness. We can see this web today in galaxy surveys that map the positions of millions of galaxies across vast volumes of space. The resulting three-dimensional maps are breathtaking, revealing a delicate, lace-like structure that stretches across billions of light-years. But how do we know this intricate web truly grew from those tiny quantum seeds? We can witness this evolution not just by looking out into space, but by running the universe in reverse inside a supercomputer. Cosmologists create virtual universes in silicon, starting with a smooth, hot plasma imprinted with a random, scale-invariant pattern of fluctuations, exactly what inflation predicts. They program in all the known laws of physics, the gravity of both dark and ordinary matter, the hydrodynamics of gas, the feedback from exploding stars. Then they press play. As the simulation runs, spanning billions of years in a matter of days, they watch the initial fuzz crystallize. The same process unfolds, the dark matter clumping first, drawing in the gas, igniting virtual stars, and forming galaxies that naturally arrange themselves into filaments and clusters. The final snapshot of these simulations is uncanny. It looks, in its statistical essence, identical to the maps we make of the real universe. The virtual cosmic web mirrors the observed one. This is the grand culmination, the closing of a profound loop. It connects the most fleeting quantum event to the largest structures we can observe. The supercomputer simulation is a time machine, demonstrating that the glittering cities of galaxies we see today are the direct, grown-up descendants of subatomic whispers. The cosmic web is not a random accident. It is the signature of creation, written first in quantum code, then magnified by inflation, and finally sculpted over eons by the patient hand of gravity. The cosmic web is a structure of breathtaking scale, yet it was built by an architect we cannot see. While the quantum seeds from inflation gave the universe its initial texture, something else was needed to turn that faint blueprint into the glittering cities of galaxies we observe. That something is dark matter, the invisible scaffolding upon which all visible structure is hung. Think of it like this: if the universe were a grand cathedral, inflation provided the architectural plans, but dark matter is the steel frame hidden within the stone, providing the essential support that allows the entire edifice to stand. This mysterious substance, which neither emits nor reflects light, has a unique property that made it the universe's first builder, because it does not interact with the intense radiation that filled the early cosmos. Dark matter could begin clumping together under gravity almost immediately after the Big Bang. Ordinary matter, the protons and electrons that make up stars and planets, was not so fortunate. For hundreds of thousands of years, it was trapped in a searing plasma, constantly buffeted by photons. This pressure prevented it from collapsing into dense clumps. Dark matter, however, felt only gravity. It was free to flow into the gravitational wells of those primordial overdensities, the hills in the cosmic landscape imprinted by quantum jitters. There it began to form vast, invisible clouds called halos. These dark matter halos are not solid objects, but diffuse, spherical concentrations of this enigmatic material. Their formation was perfectly suited to the task because of what physicists call its cold and collisionless nature. Cold simply means the dark matter particles were moving slowly compared to the speed of light from the very beginning, allowing them to settle down smoothly into gravitational traps. Collisionless means the particles, unlike atoms, do not bounce off each other. They can pass right through one another, which prevents them from forming a hot, puffy cloud, and instead lets them collapse into dense, tight cores. This behavior is the key to the filamentary web. As gravity worked on the inflationary seed pattern, the cold, collisionless dark matter didn't just form isolated blobs. It naturally streamed along the lines of the initial density field, flowing into valleys and pooling at the intersections, weaving a three-dimensional skeleton of filaments and nodes. This process created a gravitational landscape of deep wells and gentle ridges long before the first star ever shone. Only much later, once the universe had cooled and expanded, could ordinary matter, often called baryonic matter, finally respond. Freed from the pressure of radiation, the hydrogen and helium gas could now feel the relentless pull of these pre-existing dark matter concentrations. It cascaded into the halos, swirling, compressing, and eventually igniting into the first brilliant stars. Every galaxy we see, from majestic spirals to giant ellipticals, is embedded at the heart of one of these immense dark matter halos. The synergy here is profound and essential. The nearly scale-invariant spectrum of seeds from inflation provided the perfect initial conditions, a blueprint with structure at every scale. The unique properties of cold dark matter provided the perfect construction material, one that could begin assembling that blueprint efficiently and robustly. Without dark matter's early, decisive action, gravity's work on ordinary matter alone would have been too slow and too weak. The galaxies we see would be fewer, smaller, and scattered randomly, not arranged in the magnificent, large-scale web we observe. This partnership links the very largest scales of cosmic destiny, set by inflation in the first instant, to the very smallest scales of particle physics, in the unknown nature of the dark matter particle itself. Our entire visible universe, in all its splendor, is just the luminous decoration on an invisible framework, a framework whose foundations were laid in the quantum chaos of creation. A powerful theory must leave its footprints in the data, ready to be found or refuted. Inflation has done exactly that, making a series of bold, testable predictions about the universe we should see today. Its first great triumph was the geometric flatness of the cosmos, confirmed by the pattern of the cosmic microwave background to a precision of better than 1%. Its second was the nearly scale-invariant Gaussian spectrum of primordial fluctuations, a fingerprint that matches the CMB data with stunning fidelity. These are not minor details, they are fundamental architectural features of our reality, and their confirmation has made inflation the leading paradigm for our cosmic origins. Yet the story does not end with these successes. The true strength of a scientific idea is also measured by how it responds to challenge and refinement. Inflation in its current form is not a single monolithic theory. It is a broad framework, a powerful mechanism that can be realized through many different models, each proposing a slightly different shape for the Inflaton field's energy landscape. Some models predict a stronger signal of primordial gravitational waves than others. Some suggest slight deviations from perfect scale invariants. This leads to what some physicists call the measurement problem of inflation. With so many possible variations, how do we determine which, if any, is the one that actually describes our universe's birth? Critics argue this flexibility makes inflation less a definitive theory and more a versatile scenario that can be adjusted to fit almost any observation. It is a valid concern, one that the scientific community takes seriously. The response is not to abandon the idea, but to sharpen the tests. The ongoing, painstaking hunt for primordial B-mode polarization in the cosmic microwave background is the most direct way to cut through this thicket of models. Detecting that telltale swirl would be a monumental discovery, pointing strongly to a specific class of inflationary models and giving us a direct glimpse of the universe's violent first tremors. But what if, after decades of searching with ever more sensitive instruments, we never find it? That null result would be just as profound. It would rule out a wide range of popular inflationary scenarios and force theorists to seriously consider alternatives or to refine the inflationary picture into simpler, more constrained forms. This is how science progresses, not by seeking only confirmation, but by allowing evidence to prune the tree of possibilities. The journey to understand our beginnings is a process of constant interrogation, where every prediction is a clue and every unanswered question is a guidepost, leading us closer to a true picture of that first miraculous instant. The implications of inflation reach far beyond the blueprint for our single universe. Some mathematical extensions of the theory lead to a staggering and deeply controversial possibility known as eternal inflation. Here, the story of cosmic beginnings takes a turn toward the truly infinite. The core idea rests on a quantum quirk of the Inflaton field's decay. As the field tumbled from its high-energy state to end inflation in our region of space, it did so through a process analogous to water boiling. Bubbles of the new, stable vacuum spontaneously formed and expanded at the speed of light. Our entire observable cosmos resides within one such bubble, where inflation ended and the hot Big Bang began. But in the eternal inflation picture, the quantum process is imperfect. Between these expanding bubbles, in the vast intervening spaces, the Inflaton field remains trapped in its high-energy, inflationary state. And in that state, space continues to inflate exponentially and at a rate that outpaces the expansion of the bubbles themselves. The result is a runaway, self-reproducing process. While bubbles of stable vacuum like ours constantly nucleate, the inflating space between them grows so rapidly that it never disappears. Inflation, in a sense, becomes a perpetual engine, giving birth to an endless number of disconnected bubble universes within an ever-swelling multiversal foam. This isn't science fiction, but a direct, though speculative, consequence of applying quantum mechanics to certain models of the inflationary landscape. Each of these bubble universes could be a separate cosmic domain. Crucially, when inflation ends within a bubble, the released energy might crystallize into different configurations of fundamental particles and forces. The constants of nature we hold as fixed, the strength of gravity or the mass of an electron, could be random outcomes in different bubbles. In this view, our universe, with its precise laws that allow for stars, planets, and life, is not a finely tuned miracle, but simply one possibility in an infinite ensemble where every conceivable set of physical laws is realized somewhere. This idea sparks fierce debate that stretches to the very foundations of science. Proponents argue it offers a natural, physical explanation for the apparent fine-tuning we observe, removing the need for a single, special beginning. Critics counter that it pushes cosmology into the realm of the untestable. If these other universes are forever beyond our causal horizon, separated by eternally inflating space, can we ever gather evidence for their existence? Does the multiverse theory explain our universe or merely explain it away? This controversy touches on the philosophy of science itself, questioning what constitutes a valid scientific theory when direct observation may be impossible. While eternal inflation is not a necessary prediction of all inflationary models, it stands as one of the theory's most profound and challenging implications. It forces us to confront the ultimate scale of reality and to ask whether our quest for origins leads to a single story or to an infinite library of cosmic histories, each with its own first chapter. Yet the very success of inflation demands we ask a difficult question. Could the universe's story have opened with a different first chapter? Science at its best is a conversation, not a decree, and cosmology is no exception. While inflation stands as the most compelling framework we have, it is not the only idea on the table. A handful of alternative theories propose entirely different mechanisms to create those crucial seeds and solve the horizon and flatness problems, each offering a unique vision of cosmic beginnings. One profound alternative is the concept of a cyclic universe. In this picture, there is no singular, absolute beginning. Instead, the cosmos undergoes an endless sequence of expansions and contractions. Our Big Bang was not the start of everything, but simply the most recent turning point, a great bounce from a prior phase of collapse. In some cyclic models, the universe contracts to an incredibly dense state, but not to a true singularity. As it nears this point, the fabric of spacetime becomes highly turbulent, generating random fluctuations. Then, during the subsequent expansion phase, those fluctuations are stretched out, potentially creating the scale-invariant pattern we see in the cosmic microwave background. This idea elegantly avoids the question of an ultimate beginning, suggesting an eternal, rhythmic cosmos where each cycle inherits and reprocesses the structure of the one before. Another intriguing competitor emerges from the world of string theory, known as string gas cosmology. It proposes that in the very earliest moments, the fundamental ingredients of reality were not point-like particles, but tiny, vibrating strings. At these extreme energies, the universe was compact, with all its spatial dimensions curled up. As it expanded, the winding and vibration of these strings could have generated repulsive forces and density fluctuations directly, without needing a separate Inflaton field. The predicted pattern of seeds can differ subtly from inflations, offering a potential test if our observations become precise enough. Then there are various bouncing models, which share the cyclic idea of a prior contracting phase, but often focus on a single bounce event rather than an endless cycle. These models rely on modifications to Einstein's gravity or new quantum geometric effects to reverse a collapse into an expansion, again using the dynamics of the bounce to imprint the necessary irregularities. What unites these alternatives is their ambition to address the same cosmic puzzles without invoking a period of exponential inflation. Their key differences are profound. Most avoid a true beginning from nothing, offering instead a transformation from a prior state. They often predict different detailed statistics for the primordial fluctuations, perhaps with more pronounced deviations from scale invariants or a different pattern of gravitational waves. Some might leave a distinct fingerprint in the polarization of the cosmic microwave background that future telescopes could distinguish from an inflationary signal. Examining these ideas is not an academic exercise. It is the essential engine of scientific progress. A theory that faces no competitors risks becoming complacent. The existence of viable, if less popular, alternatives keeps the field honest. It forces proponents of inflation to sharpen their predictions, to identify the unique, testable signatures that would rule out other possibilities. This rigorous comparison is how we move from a compelling story toward a confirmed history. Inflation's explanatory power is immense, but its ultimate validation lies not just in what it explains, but in surviving every attempt to explain the same facts in a different way. The quiet hum of alternative theories in the background is the sound of science doing its job, ensuring that our cosmic origin story is built not on convenience, but on evidence that withstands all challenges. Our quest to read the universe's first chapter is a story of human ingenuity. It demands instruments of almost impossible sensitivity, built to detect whispers from the edge of time itself. To translate the ancient light of the cosmic microwave background, we needed a cosmic photographer operating in the perfect silence of space. The European Space Agency's Planck satellite was exactly that. Launched in 2009, it was a technological masterpiece designed to map the faint afterglow of the Big Bang in microwave light with a precision never before achieved. Its instruments were cooled to just a fraction of a degree above absolute zero to eliminate their own heat from contaminating the signal. For over 4 years, it scanned the entire sky, patiently collecting photons that had traveled for 13.8 billion years. The data it beamed back gave us our sharpest ever baby picture of the universe, a map of temperature variations so detailed it allowed scientists to measure the cosmos's age, composition, and geometry with breathtaking certainty. Planck did not just see the forest of primordial seeds, it counted every single tree, confirming the inflationary blueprint in exquisite detail. But to hunt for the even fainter signal of primordial gravitational waves, scientists must go to one of the most hostile environments on Earth. At the South Pole, the air is cold, dry, and stable for months on end, offering a crystal-clear window to the cosmos. Here, experiments like the BICEP array and the Keck telescopes stand as sentinels in the endless white. These are not traditional telescopes with large mirrors, but arrays of specialized radio receivers, their detectors chilled to within a whisper of absolute zero. They stare at a single patch of sky for years, measuring not temperature, but the subtle polarization of the ancient light. Their mission is to filter out the foreground noise of our own galaxy's dust, listening for the faint, swirling pattern that would be the signature of spacetime's first tremors. This work is painstaking, a monumental effort in engineering and data analysis conducted by international teams working in unison. Yet our time machines do not only look back in light, they also map the present to understand the past. To see how the quantum seeds grew into the cosmic web, we must chart the universe's current large-scale structure. Projects like the Dark Energy Spectroscopic Instrument, DESI, and the European Space Agency's Euclid Space Telescope are engaged in this grand cartography. DESI, mounted on a telescope in Arizona, is not taking pretty pictures. It uses 5,000 robotically controlled fibers to capture the light of millions of galaxies simultaneously, measuring their distances to build a three-dimensional map of the universe spanning 11 billion light-years. Euclid, from its vantage point in space, will image billions of galaxies to trace the influence of dark matter and dark energy on the Webb's evolution. These surveys are creating a living family tree for cosmic structure, allowing us to run the film of cosmic evolution backward and forward, testing if the grown-up universe truly matches the predictions born from its infant blueprint. These technological marvels, from the frozen plains of Antarctica to the vacuum of space and mountaintop observatories, represent a global collaboration of thousands. They are the bridges we have built between brilliant theoretical prediction and hard empirical fact, turning the philosophical wonder of our origins into a measurable, testable science. They are proof that by extending our senses with silicon and steel, we can witness the very first moments of everything, hearing the echoes of creation in the cold silence of the cosmos. These grand cosmic experiments are mirrored by a quieter, but no less revolutionary, quest happening here on Earth. Inside highly controlled laboratory chambers, physicists are building miniature universes in an attempt to recreate the physics of creation itself. We cannot rewind time and witness cosmic inflation directly, but we can engineer analog systems that obey similar mathematical rules, creating what some call tabletop cosmology. The most promising of these experiments work with a bizarre state of matter known as a Bose-Einstein condensate. By cooling a cloud of atoms to just a whisper above absolute zero, scientists can make the atoms lose their individual identities and merge into a single quantum wave. This superfluid behaves in ways that mimic the dynamics of an expanding universe. Researchers can then precisely manipulate this condensate, using lasers and magnetic fields to simulate an expansion of space. As they trigger this controlled expansion, they can watch what happens to the quantum fluctuations within the condensate. Just as quantum jitters in the Inflaton field were stretched into cosmic seeds, the tiny fluctuations in the condensate are amplified by the simulated expansion, creating patterns of density ripples that can be directly observed and measured. It is a breathtakingly direct test of the core inflationary mechanism, watching quantum noise transform into larger structure, all within a device smaller than your thumb. Other ingenious experiments use superconducting circuits, the same technology behind quantum computers. These circuits can be designed to behave like an abstract quantum field in a curved spacetime. By sending precisely tuned microwave pulses through the circuit, physicists can simulate the sudden expansion of the universe and study how particle pairs, like those theorized to emerge from the quantum vacuum during inflation, are generated. These are not mere simulations on a computer screen. They are physical systems where the laws of quantum field theory in a dynamic space are played out in real time, with all the unexpected noise and complexity that a purely theoretical calculation might miss. This work represents a beautiful convergence of scientific disciplines. Cosmologists who study the largest things imaginable are collaborating with condensed matter physicists who master the quantum behavior of materials. They have discovered that the mathematics describing the birth of the universe can also describe the behavior of ultra-cold atoms or flowing electrons in a crystal. This means the profound physics that shaped the cosmos is not locked away in the distant past. It is woven into the fabric of reality at every scale, waiting to be uncovered in a lab. While these analog experiments cannot tell us the exact details of our universe's inflation, they serve as vital validators. They test whether the fundamental process of amplifying quantum fluctuations through rapid expansion actually works as our theories predict. They provide a tangible, experimental sandbox where we can probe the edge of our understanding, offering a unique glimpse into the quantum mechanics of creation from the comfort of our own world. This cosmic story forces a profound question about our own place within it. If the grand tapestry of galaxies was woven from subatomic randomness, what does that say about us? Are we, and everything we see, simply the long-term consequence of a quantum accident? The answer is not a simple yes or no, but a layered revelation about the nature of the universe itself. On one hand, the initial conditions were indeed set by chance. The specific pattern of hills and valleys in that primordial density field was random, a frozen snapshot of quantum static. In that sense, the particular address of our Milky Way galaxy within the cosmic web, the specific distribution of stars in our corner of space, can be traced back to a roll of the dice in the first fraction of a second. There is an undeniable element of contingency, an acknowledgement that things could have turned out differently, yet to call it merely random misses the breathtaking second half of the story. Once those seeds were sown, the universe unfolded with a powerful, deterministic logic. The laws of physics, gravity, nuclear forces, electromagnetism are not random. They are the unwavering rules of the game. Given those specific initial seeds and those immutable laws, the emergence of planets, stars, and galaxies was not an accident but an inevitable outcome. The dice were rolled, but the rules of the game guaranteed that structure would arise. This interplay between chance and necessity is a central theme in nature, from the evolution of life to the formation of snowflakes. A philosopher might look at this and see a universe that is creative precisely because it has both elements: the spontaneous gift of initial variety and the reliable machinery to build upon it. For many scientists, this narrative does not diminish meaning but redefines its source. The meaning is not in a preordained, detailed blueprint, but in the magnificent, emergent process itself. The fact that simple, elegant laws can take quantum noise and, over billions of years, transform it into a planet that can contemplate its own origins, that is a story filled with a different kind of awe. It suggests a cosmos where the potential for complexity and even consciousness is written into the fundamental fabric of reality, waiting only for the right conditions to unfold. Our existence is not a random fluke in a meaningless void, but a testament to a universe that is inherently fruitful, capable of generating islands of order and beauty from a sea of chaos. The quantum dice were rolled, but they were loaded in favor of creation. But for all its explanatory power, inflation is not a finished story. It is a brilliant opening chapter that raises even deeper mysteries about the nature of reality itself. The fundamental identity of the Inflaton field remains perhaps the greatest unknown. Was it a unique, fundamental force of nature that operated only in that first instant? Or is it a manifestation of something deeper, perhaps a property of space or a relic from a theory of everything? We do not know what this field truly was, only what it did. This leads directly to the next profound puzzle, the question of initial conditions. What, if anything, came before inflation? How did that tiny patch of space get into the false vacuum state to begin with? Was it a quantum fluctuation from an even earlier era, or a fragment of a previous cosmic cycle? Inflation elegantly describes what happened once it started, but the trigger for the process itself remains hidden in the realm of quantum gravity, a domain where our current laws of physics cease to provide answers. These are not minor gaps, they are chasms in our understanding, pointing toward the need for a more complete theory. The ultimate goal is to move beyond a description of cosmic expansion and toward a true theory of creation, one that can address the singularity or the state from which everything emerged. This likely requires unifying the two great pillars of modern physics, quantum mechanics and general relativity, into a single coherent framework. Candidates like string theory or loop quantum gravity attempt this monumental task, and each offers different visions for what could have preceded or ignited inflation. Some suggest the universe emerged from a quantum bounce, others from a collision of higher dimensional brains. Until we have experimental guidance, these remain profound but speculative possibilities. This is why the hunt for definitive proof is so urgent. The search for primordial B-mode polarization in the cosmic microwave background is our most promising near-term test. A clear detection would be a direct line back to the energy scale of inflation, offering clues about the Inflaton field's properties, but scientists are also pursuing other, more subtle signatures. Could there be faint imprints in the distribution of galaxies, or unique patterns in the gravitational wave background that future observatories might detect? Each potential signature is a different window into that first moment. The next generation of telescopes, both on the ground and in space, are being designed with these questions in mind. They will map the cosmos with unprecedented precision, measuring the cosmic microwave background's polarization, charting billions of galaxies to trace dark matter, and listening for the faint hum of primordial gravitational waves. Their data will either confirm inflation's specific predictions with even greater certainty or reveal deviations that point to a new and unexpected beginning. The journey to understand our origins is therefore a journey into the future of physics itself. It pushes our technology to its limits and our minds to the edge of comprehension. Every unanswered question is a beacon guiding the next great discovery. In tracing the line from quantum jitters to the cosmic web, we have not reached an end, but have found a new beginning for our curiosity, a frontier where the very first instant of time awaits its final explanation. The relentless increase of disorder is one of the most fundamental rules of our reality. An egg can scramble, but it will never unscramble itself. A star radiates its light and heat into the cold void, never to gather that energy back. This one-way street is governed by the second law of thermodynamics, which states that entropy, a measure of disorder or randomness, always increases in a closed system. But this law presents a profound puzzle when we look back to the beginning. For entropy to increase for billions of years, the universe must have started in a state of astonishingly low entropy, a condition of extraordinary order and delicate arrangement. Why was the cosmic deck of cards so perfectly stacked at the start? The answer may be written in the same event that gave us galaxies. Inflation did not just create seeds of structure, it may have also wound up the cosmic clock, defining the very arrow of time. To understand this, we need to think of entropy not as messiness, but as a measure of possibilities. A broken egg has high entropy because the yolk and white can be scattered in countless different ways. A pristine, intact egg represents just one specific, highly ordered configuration among trillions of possibilities, a state of incredibly low entropy. The early universe, as revealed by the cosmic microwave background, was also in a state of remarkably low entropy. It was not a random, chaotic mess. It was incredibly smooth and uniform, a condition that is statistically very special and unlikely. This smooth beginning is the reason time has a direction. If the universe had begun in a state of maximum entropy, a featureless high-temperature equilibrium, nothing would ever happen. There would be no stars, no planets, and no flow from past to future, because everything would already be in the most disordered state possible. The fact that we see change, structure, and history unfolding means the cosmos started wound up like a colossal spring and has been unwinding ever since. This is where inflation provides a powerful and elegant explanation. Recall that before inflation, our observable universe was smaller than a single atom, a realm where quantum gravity reigns and our current notions of order and disorder may not even apply. It could have been a chaotic, fluctuating foam of spacetime. Inflation acts as a cosmic reset button for entropy. That exponential expansion takes whatever pre-inflationary state existed, no matter how messy or complex, and stretches it to an immense scale. This process does two crucial things. First, it smooths everything out. Any large-scale lumps, wrinkles, or temperature differences are stretched so thin they become negligible, creating that uniform, low-entropy condition we see in the CMB. Second, it flattens the geometry of space. Think of it like taking a wildly crumpled piece of paper and stretching it so tightly in all directions that it becomes perfectly flat and smooth. The act of inflation itself creates a vast, simple, and ordered starting point by erasing the complexity of whatever came before. In this view, inflation did not begin with low entropy, it produced it. The immense gravitational repulsion of the false vacuum did the work of organizing the cosmos, creating a clean slate of smooth space and uniform energy. When inflation ended and that energy decayed into a hot plasma of particles, the universe was left in a spectacularly low entropy state, poised to begin its long, irreversible journey toward greater disorder. The arrow of time was set. Every process that has followed, from the nuclear fusion in the first stars to the chemical reactions in your cells, is part of that grand unwinding. The increase in entropy is the engine that drives change, and it was ignited by inflation's great smoothing. This connection ties the origin of everything we see to the most intimate experience of our lives, the relentless forward march of time. The same quantum fluctuations that seeded galaxies also represent the first tiny steps away from perfect order, the initial whispers of the disorder that would grow to shape cosmic history. We are not just children of the stars, we are children of that primordial winding of the cosmic spring. Our ability to remember the past but not the future, to see causes lead to effects, may find its ultimate origin in that brief, violent burst of expansion that created both a smooth universe and the direction of time itself. These scientific insights do not remain locked in journals and equations. They escape into our shared culture, becoming a new kind of origin story for a modern world. The tale of cosmic inflation and quantum genesis has woven itself into the fabric of our storytelling, offering a scientifically grounded creation myth that resonates deeply in a secular age. You can find its echoes in the grand visuals of planetarium shows and major documentary series, where supercomputer simulations of the cosmic web unfurl across giant screens, translating data into a spectacle of light and sound that evokes a profound sense of scale. The language of cosmology has permeated science fiction, providing a tangible backdrop for narratives about existence. Stories might feature ancient artifacts imprinted with the polarization pattern of the cosmic microwave background, or civilizations tracing their lineage not to a single planet, but to a specific density fluctuation in the primordial soup. These are not just plot devices, they are reflections of a fundamental shift in how we conceive of our beginnings. For millennia, human cultures have looked to the stars and told stories of gods, heroes, and great beings who shaped the cosmos from chaos. Today, we have a different, yet no less epic, narrative. It is a story where the protagonists are invisible fields and probabilistic waves, where the heroic act is an exponential expansion, and the legacy is a universe structured by amplified whispers. This narrative fulfills a deep human need to situate ourselves within a grand chronology, to understand our lineage. It tells us we are not merely placed in the universe, but that we are literally made from its most ancient processes. The iron in our blood was forged in the hearts of stars that themselves formed because of gravitational seeds from the dawn of time. This connection transforms the cosmos from a distant spectacle into an ancestral home. The cultural impact of this is profound. It fosters a unique blend of humility and significance. We are humbled by the sheer scale and the role of chance, recognizing that our specific corner of existence was not preordained. Yet we are also granted significance by the understanding that the universe, through its fundamental laws, possesses an inherent creativity capable of generating complexity, consciousness, and creatures who can trace their origins back to the first moment. This cosmological story shapes our collective sense of place, offering a framework for wonder that is continually refined by discovery. It reminds us that our drive to tell stories about the cosmos and our quest to scientifically understand it are, at their heart, the same beautiful human impulse to look up and ask where we came from, and to find in the answer a deeper connection to everything that is. Clarifying what inflation is not can be as important as understanding what it is. One of the most common points of confusion is the relationship between inflation and the Big Bang. They are not the same event. The Big Bang describes the hot, dense, expanding state of the universe that has existed for nearly 13.8 billion years. Inflation was a fleeting episode that occurred within the first sliver of a second of that timeline, a spectacular prologue that set the stage for the traditional hot Big Bang to follow. Think of it like the starting engine of a grand rocket. Inflation was the explosive ignition, the sudden, violent burst that cleared the launch pad. The hot Big Bang is the long, sustained journey of the rocket itself, coasting on the momentum and conditions established at liftoff. Another frequent question involves the ultimate speed limit. How could space expand faster than light without breaking Einstein's rules? The key distinction is that nothing is moving through space faster than light. Instead, it is the fabric of space itself that is stretching. The speed of light limit applies to objects traveling within the universe, not to the expansion of the stage upon which they stand. A useful analogy is baking raisin bread. As the dough rises, the raisins move apart from each other. No single raisin is zooming through the dough, but the space between them grows because the entire loaf is expanding. If the dough rose quickly enough, two raisins could become separated by a distance that light, traveling through the dough, could not cross in a given time. That is the essence of inflationary expansion, a stretching of the cosmic canvas itself. We also need to be precise about those quantum seeds. When we say quantum fluctuations, we are not talking about literal particles popping into existence like tiny fireworks. The process is more subtle and fundamental. It involves the Inflaton field, that energy landscape that drove the expansion. Even in its lowest energy state, a quantum field is never perfectly still. It experiences tiny, random variations in its value, like the surface of a pond shimmering with unseen ripples. These are fluctuations in the field's energy density, momentary hills and valleys in an otherwise flat plane. During inflation, these hills and valleys were not particles being created, but rather probabilities being stretched into permanent cosmic geography. They became the template for where matter would eventually condense. Finally, while the idea of a multiverse is a thrilling and widely discussed implication, it is crucial to separate established theory from speculative extension. Inflation, as a mechanism to solve the horizon and flatness problems and generate seeds, is strongly supported by evidence like the cosmic microwave background. The leap to an eternal, bubble-producing multiverse is a consequence of applying quantum mechanics to certain, but not all, models of inflation. It is a fascinating mathematical possibility that some versions of the theory suggest, not an inevitable conclusion of the theory itself. Distinguishing between the well-tested core and its more speculative branches keeps our feet grounded in evidence while allowing our minds to wander the frontiers of possibility. This clarity ensures that our wonder is directed by understanding, not by misconception. Behind every revolutionary equation lies a story of human insight. Alan Guth's notebook entry was a pivotal moment, but the theory of inflation was shaped and refined by a vibrant community of thinkers, each adding a crucial piece to the puzzle. Shortly after Guth's initial proposal, a young physicist in Moscow named Andrei Lind took the idea in a breathtaking new direction. While Guth envisioned a single, smooth transition, Lind introduced the concept of chaotic inflation, suggesting the Inflaton field could have started from a wide range of initial values in different patches of space. This was a more flexible and powerful framework, and it naturally led him to a staggering implication: the possibility of eternal inflation and a multiverse. Lind's journey, working within the constraints of the Soviet scientific system before moving to the West, embodies the universal and relentless nature of curiosity. His contributions turned a clever mechanism into a rich, multifaceted theory. Alongside these builders were the rigorous testers and sometimes the thoughtful critics. Paul Steinhardt was one of inflation's earliest and most enthusiastic contributors, helping to develop the new inflationary model that solved technical issues in Guth's original version. Yet, as the theory evolved toward ideas like eternal inflation, Steinhardt became one of its most prominent questioners. His critique is not born of skepticism for its own sake, but from a deep concern for testability and what constitutes a truly scientific explanation. His advocacy for alternatives like the cyclic universe ensures the conversation remains dynamic and self-critical. This dialogue between creation and critique is not a weakness of cosmology, it is its greatest strength. It is how ideas are tempered and refined. Beyond these well-known names are thousands of other researchers whose work translates theory into fact. They are the engineers who build the satellites, the programmers who write the analysis codes, and the astronomers who spend years at remote observatories, their faces lit by the glow of monitors as they sift through petabytes of cosmic data. The meticulous maps from the COBE, WMAP, and Planck missions are not the product of a single mind, but of vast international collaborations where meticulous care and shared purpose are paramount. Think of the teams at the South Pole, enduring months of darkness and extreme cold to tend to delicate instruments, all to capture a whisper of signal from the dawn of time. Their stories are less often told, but they are the bedrock of discovery. These personal journeys, marked by late-night insights, spirited debates at conferences, and decades of patient work, remind us that cosmology is a profoundly human endeavor. It is driven by the same qualities found in any great exploration: curiosity that looks at the smooth night sky and senses a hidden story, perseverance to spend a career chasing a signal one might never see, and a collective spirit that knows the universe is too big a mystery for any one person to solve alone. The blueprint of the cosmos may be written in quantum code, but it is decoded by human hands, hearts, and minds, forever reaching for the stars to understand their and our extraordinary beginning. This synthesis of scales is perhaps the most profound legacy of inflation. For a fleeting instant, the universe existed in a realm where the rules of the very small and the laws of the very large were not just connected, but were speaking the same language. Quantum mechanics, which governs the probabilistic dance of particles and fields, directly dictated the gravitational landscape of the entire cosmos through general relativity. This happened long before we have a complete theory of quantum gravity, yet inflation gives us a precious glimpse into how that ultimate unification might work. Think of it as a cosmic experiment that already ran, leaving its results imprinted across the sky for us to decode. In that first fraction of a second, the behavior of a single quantum field, with all its inherent fuzziness and uncertainty, became the architect of spacetime itself. The microscopic jitters in the Inflaton field were not just minor details, they were the source code. When stretched by inflation, those quantum probabilities transformed into concrete variations in the density of matter, which then curved the fabric of the universe through gravity. It's a direct chain of cause and effect, where a quantum event sets a gravitational condition that lasts for billions of years. This means the majestic spiral of a galaxy, governed by gravity on an enormous scale, can trace its lineage back to a random tremor in a field that obeyed the rules of the quantum world. We are seeing, in the detailed map of the cosmos, a frozen moment where these two great theories held a conversation. Studying inflation is like finding a recorded transcript of that conversation. By analyzing the statistical pattern of the cosmic seeds, we are indirectly probing the physics of that extreme union. The nearly scale-invariant spectrum we observe is not just a feature of the expansion, it's a signature of how quantum fields behave when stretched across an exponentially growing spacetime. Each detail in the cosmic microwave background is a clue about the quantum nature of gravity itself. So the quest to understand our cosmic origins is also a journey toward a deeper theory of everything. By looking out at the largest structures, we are peering back into a domain where the smallest rules created the largest canvas, a beautiful reminder that the universe is not divided, but profoundly whole. The quest to hear the universe's first whispers does more than satisfy our curiosity. It forces us to build tools of almost impossible sensitivity, and those tools, in turn, quietly reshape our world. While understanding cosmic inflation will not help you download a faster app or stream a sharper video, the relentless drive to test this theory has become a powerful engine for technological innovation, spinning off breakthroughs that touch our daily lives in unexpected ways. Consider the monumental challenge of mapping the cosmic microwave background. To capture that ancient signal, we must detect temperature variations of a few millionths of a degree, a feat that requires eliminating every source of interference, including the heat from the instruments themselves. This necessity has pushed the frontiers of cryogenics, the science of extreme cold. Satellites like Planck house detectors cooled to just 1/10 of a degree above absolute zero. Developing the technology to achieve and maintain such profound cold in the harsh environment of space has led to advances in refrigeration systems, ultra-stable materials, and thermal insulation. These innovations now find critical applications in medicine, where they improve the cooling for MRI machines, making them more powerful and efficient, and in preserving biological samples for research. Another quiet revolution born from this cosmic hunt is in the realm of low-noise amplifiers. The faint microwave photons from the edge of time carry an incredibly weak signal, easily drowned out by electronic static. To hear them, engineers had to invent amplifiers with almost no internal noise, devices that can boost a whisper without adding their own hiss. The technology developed for telescopes at the South Pole and for space-based observatories has directly influenced the design of satellite communications and medical imaging devices. It enhances the clarity of signals from deep space probes and can improve the sensitivity of diagnostic equipment that listens for faint physiological signals within the human body. Perhaps the most widespread spin-off lives in the world of data. A single CMB mapping mission can generate petabytes of raw data, a cosmic haystack in which we must find the subtlest of needles. Processing this deluge requires sophisticated algorithms and pattern recognition techniques. Cosmologists were among the early pioneers in applying machine learning to sort signal from noise, to clean images of foreground interference from our galaxy, and to extract the underlying statistical patterns. The tools and methods refined for analyzing the universe's baby picture are now foundational in fields far removed from astronomy. They help meteorologists model complex climate systems, enable financial institutions to detect subtle patterns in markets, and allow medical researchers to identify early signs of disease in vast scans of medical imagery. This is the beautiful, indirect yield of fundamental research. By asking the biggest questions with no obvious practical aim, we are forced to invent new ways of seeing, measuring, and thinking. The technological muscles we build to comprehend the cosmos become tools for solving earthly challenges. The pursuit of cosmic origins does not just tell us where we came from, it expands what we are capable of doing right here, right now, demonstrating that the drive to understand the universe is, itself, a profound and practical human endeavor. The precise texture of our cosmic blueprint carries a startling implication. The strength of those primordial quantum seeds, the amplitude of the fluctuations we measure in the cosmic microwave background, is not arbitrary. It sits within a remarkably narrow window that allows for a universe like ours to exist. If the initial density variations had been significantly stronger, the story of cosmic structure would have taken a dark and swift turn. Gravity would have acted with overwhelming ferocity on those over-dense regions. Instead of gently pulling gas into halos to form stars, it would have immediately crushed vast amounts of matter directly into black holes. The universe would be a terrifying landscape of singularities, a cosmic graveyard devoid of the stable, long-lived stars necessary for planets and chemistry. Conversely, if the quantum seeds had been much weaker, the opposite fate would have unfolded. Gravity's grip would have been too feeble to ever overcome the expansion of space. Those subtle overdensities would have simply dissipated, never condensing into galaxies. The cosmos would have remained a forever smooth, ever-thinning haze of hydrogen and helium, a luminous but utterly featureless fog with no islands of matter complex enough to ever ponder its own existence. Our universe, with its gentle hills and valleys, its balanced rate of clumping, exists in a cosmic sweet spot. It is powerful enough to build grand structures, yet patient enough to build them slowly and stably over billions of years, providing the time needed for stars to forge heavy elements and for planetary systems to coalesce. This fine-tuned balance leads to a profound and often debated line of reasoning known as the anthropic principle. In its simplest form, it states that we can only observe a universe with properties that allow for observers to exist. We are not separate from the cosmos we measure, we are a product of it. Therefore, the fact that we find ourselves in a universe with fluctuations of just the right amplitude is not a bizarre coincidence we must explain away, but a necessary condition for us to be here asking the question in the first place. This shifts the perspective from why is the universe this way to what must the universe be like for us to be in it. For some, this reasoning feels like a philosophical tautology, a way of avoiding a deeper explanation. For others, it is a crucial insight into the nature of scientific inquiry when applied to the universe as a whole. The anthropic principle gains substantial weight when paired with the concept of a multiverse arising from eternal inflation. If an endless cosmic foam of bubble universes is real, and each bubble crystallizes with different random values for its fundamental constants and initial conditions, then most bubbles would be stillborn or barren. They might flash into existence and remain empty or immediately collapse into chaos. But in a vast enough ensemble, a tiny fraction of bubbles will, by pure chance, have the precise golden parameters that allow for galaxies, stars, planets, and life. We inevitably find ourselves within one of those exceptionally rare, life-permitting bubbles, not because it was designed, but because we could not find ourselves anywhere else. From this viewpoint, the fine-tuning we observe is not evidence of a guiding hand, but the inevitable statistical outcome of a process that generates every possible outcome. Our existence becomes the selection effect that explains why we see the particular cosmic lottery ticket we hold. This does not close the book on why our universe is the way it is, but it reframes the mystery, connecting the quantum origins of structure to the deepest questions of our place in a potentially infinite reality. The James Webb Space Telescope is not just a time machine to the first stars, it is a forensic instrument for cosmic origins. By capturing the faint infrared light of the earliest galaxies, it allows us to watch the very first chapters of structure formation unfold. How quickly did those initial quantum seeds blossom into luminous cities of stars? The timing, size, and distribution of these primordial galaxies are a direct test of the inflationary blueprint. If the seeds were laid down as predicted, then the growth of these first structures should follow a specific, calculable timeline. Webb's unprecedented power lets us measure the masses and ages of galaxies that existed when the universe was only a few 100 million years old, providing a crucial data point to check if gravity's work matches the story written in the quantum fluctuations. Any significant deviation, such as galaxies that are too massive or too mature too early, would send a tremor through cosmology. It could indicate that the initial conditions were not exactly as we think, or that unknown physics influenced the early growth of dark matter halos, forcing us to re-examine our models from the first instant forward. But Webb is only the beginning of a new golden age of cosmic cartography. Looking ahead, the Nancy Grace Roman Space Telescope, set to launch later this decade, will take a panoramic view. Where Webb looks deeply at a narrow patch of sky, Roman will conduct a vast, wide-field survey, mapping the distribution of galaxies and galaxy clusters across cosmic time with Hubble's sharpness, but over an area 100 times larger. This immense statistical power will allow scientists to trace the evolution of the cosmic web in exquisite detail, measuring how filaments and nodes grew from the infant universe to the present day. It will also peer into the nature of dark energy, the mysterious force accelerating expansion today, but in doing so, it will provide an even more stringent test of the initial conditions that set everything in motion. By comparing the observed large-scale structure against supercomputer simulations that start with inflationary seeds, Roman can reveal subtle mismatches, tiny cracks in the standard model that might point toward new physics operating in the universe's first moments. Perhaps the most revolutionary tool on the horizon listens not for light but for spacetime's vibrations. The Laser Interferometer Space Antenna, or LISA, is a future European Space Agency mission that will open an entirely new sense, the direct detection of low-frequency gravitational waves. While ground-based observatories hear the high-frequency chirps of merging black holes, LISA will listen for the steady hum of monstrous binaries, the ripples from supermassive black holes orbiting each other in the hearts of distant galaxies. But its potential extends even further back. LISA might be sensitive enough to detect a faint, background rumble of gravitational waves from the earliest universe. This could include signals from cosmic strings, hypothetical defects in spacetime, or, most tantalizingly, the amplified quantum tremors of the Inflaton field itself. A confirmed detection of this primordial gravitational wave background would be the ultimate smoking gun for inflation, a direct soundtrack to the universe's birth pangs. Even its absence, measured with LISA's precision, would powerfully constrain which inflationary models could possibly be correct, potentially ruling out whole classes of them. Together, these observatories represent a multi-pronged assault on the mystery of beginnings. They will stress-test the inflationary paradigm from every angle, using the first galaxies, the full map of the cosmic web, and the vibrations of spacetime as independent witnesses. The goal is not merely to confirm what we already suspect, but to discover the anomalies, the data points that stubbornly refuse to fit. It is in those stubborn discrepancies that new physics often hides. A strange pattern in the earliest galaxies, an unexpected feature in the clustering of matter, or a missing gravitational wave signal could be the clue that points us toward a deeper theory, perhaps one that modifies inflation or replaces it altogether with something even more profound. We are building tools not to end a story, but to find the plot twists that will write its next chapter, guiding us closer to a true understanding of that first, unimaginable instant when everything began. The final proof lies in running the universe in reverse. To truly connect the quantum whisper to the galactic shout, we must watch the story unfold from start to finish, and for that we turn the cosmos into code. Inside the world's most powerful supercomputers, cosmologists build entire universes from scratch, in a field known as computational cosmology. This is not science fiction, but a rigorous laboratory where the equations of our theories are put to the ultimate test. Projects with names like Illustris TNG, Millennium, and Achu are not just simulations, they are digital twins of reality, tracing 13.8 billion years of cosmic history in a matter of weeks. They begin with a simple, smooth expanse of virtual space, imprinted with a very specific pattern of faint density variations. This starting point is not random. It is the precise, nearly scale-invariant spectrum of primordial seeds predicted by cosmic inflation. Into this digital canvas, programmers pour all the known laws of physics, the relentless pull of gravity from both dark and ordinary matter, the complex hydrodynamics of swirling gas, the explosive feedback from supernova, and the growth of supermassive black holes. Then they press play. What unfolds is a breathtaking ballet of creation. At first, the simulation shows only a faint cosmic static, a gentle fuzz of light and dark. But as the digital clock ticks forward, gravity begins its patient work. The dark matter, cold and collisionless, flows first. It streams along the invisible contours of the initial density field, weaving a three-dimensional skeleton of delicate filaments. At the intersections of these filaments, matter pools into dense knots, the future sites of immense galaxy clusters. This emerging cosmic web is the dark matter scaffold, and it forms with a stunningly natural elegance from those inflationary beginnings. Next, the ordinary matter, the baryonic gas, responds. It cascades into the gravitational wells carved by the dark matter, spiraling and compressing. In the densest cores, conditions reach a critical point, and the simulation's algorithms trigger the birth of stars. Pinpricks of light ignite across the dark web. These first stars live fast and die young, their violent deaths blasting heavy elements back into the surrounding gas, enriching it for the next generation. Galaxies begin to coalesce, merging and growing as they slide along the dark matter filaments, piling up at the great intersections. The simulation does not just show a static picture, it is a dynamic film. We can watch a single galaxy form, seeing it start as a tiny ripple in the initial data, grow through repeated mergers with its neighbors, and eventually settle into a majestic spiral, its swirling arms filled with virtual stars born from the recycled material of countless stellar generations. We can zoom out to see the entire cosmic web, a vast, evolving sponge of light and shadow that stretches across billions of light years. The most profound moment comes at the end. Researchers freeze the simulation at the present cosmic day, a digital snapshot of a universe 13.8 billion years old. They then compare this virtual cosmos to our own. They create synthetic surveys mimicking what our telescopes like Hubble or the Sloan Digital Sky Survey would see if they were pointed at the simulation. The comparison is uncanny. The statistical properties match: the way galaxies cluster together, the abundance of giant clusters versus small groups, the very texture of the large-scale structure, all align with remarkable fidelity with the maps we have made of the real universe. This agreement is the closing of a monumental loop. It demonstrates that the chain of causality we have theorized is not just elegant, it is functionally real. Given those specific quantum initial conditions and the known laws of physics, the universe we see is not just a possibility, it is the expected outcome. These simulations do more than confirm, they also reveal. They allow scientists to run experiments that are impossible in reality. What if dark matter were slightly warmer? What if the strength of the primordial seeds were different? By tweaking the initial parameters and the underlying physics, researchers can see how the cosmic web changes. This helps interpret puzzling observations and guides the search for new physics. When our telescopes see something unexpected, like a galaxy that seems too massive for its age, we can plug that mystery into the simulation to see what early universe conditions might have produced it. Supercomputer simulations have become the essential third pillar of modern cosmology, standing alongside theory and observation. They are the bridge that turns abstract equations and fuzzy telescope images into a coherent, dynamic story. They allow us to witness with our own eyes the magnificent consequence of a quantum genesis, watching as the faintest imprint of inflation blossoms into the glittering, filamentary universe we call home. In these digital realms, we hold the history of everything from the first instant to the present day, and find that the code we write mirrors the cosmos we see, a powerful testament to the fact that we are finally beginning to read the universe's first chapter correctly. Yet this grand quest for cosmic origins is not merely a technical one. It raises a deeper, more human question. In a world with immediate and pressing needs, from health challenges to environmental concerns, why should we devote such immense effort and resources to understanding events that lasted less than a trillionth of a second, over 13 billion years ago? The answer lies not in a practical application, but in the profound value of pure, curiosity-driven exploration. This is science not for what it builds, but for what it reveals about us and our place in the cosmos. The drive to understand our beginnings is one of humanity's oldest and most defining traits. We are storytellers by nature, and cosmology provides our species with its most expansive origin story, grounded not in myth but in evidence. It fulfills a deep-seated need to know where we came from, to trace our lineage not just through family trees or fossil records, but back to the very first moments of time and space. This pursuit enriches our culture in immeasurable ways. It inspires art, music, and literature, feeding our collective imagination with visions of cosmic dawn and the vast architecture of reality. It demonstrates the breathtaking power of the human intellect, that a species born on a small rock can decipher the history of the entire observable universe using nothing but mathematics, ingenuity, and the light from ancient stars. This journey also teaches a vital humility. By revealing the sheer scale of cosmic time and our planet's minute place within it, cosmology offers a perspective that transcends our earthly divisions. It reminds us that every human life, every civilization, and every triumph and hardship has unfolded on a single, fragile world adrift in a vast and ancient cosmos. This cosmic perspective, famously called the pale blue dot view, can foster a sense of shared stewardship for our one and only home. Ultimately, the quest to understand inflation and the quantum seeds of existence is a celebration of curiosity for its own sake. It is a testament to what we can achieve when we allow our minds to wander the deepest mysteries, not because it will power our cities or cure illness, but simply because the questions are there, waiting to be asked. This unrestrained exploration of the unknown is one of the highest expressions of our humanity, proving that we are creatures who look at the stars and dare to wonder how we belong to their story. From that first, unimaginable whisper to the vast galactic cities we see today, our cosmic story is one of magnificent transformation. We have traced a direct line from the quantum foam of the primordial universe to the grand cosmic web of galaxies, revealing an astonishing narrative of order born from chaos. Cosmic inflation, with its violent, exponential expansion, provided the perfectly smooth canvas, stretching a subatomic speck into our entire observable cosmos. And within that furious stretching, the tiniest quantum fluctuations, the inherent jitter of reality itself, were caught and magnified. They became the brushstrokes, the essential imperfections that gravity would use to sculpt every star, every galaxy, and every filament of light in the dark. This is not a philosophical metaphor, but a physical chain of cause and effect supported by a wealth of evidence. The cosmic microwave background shows us the fossilized imprint of those seeds. The large-scale surveys of galaxies reveal the grown-up structure that resulted. The supercomputer simulations demonstrate that, given those starting conditions, the universe we see is the inevitable outcome. This story stands as one of the most profound achievements of modern cosmology, a testament to human curiosity and ingenuity. It connects the realm of the impossibly small to the domain of the impossibly large, showing us that the fundamental laws of quantum physics are literally written into the architecture of the heavens. As we continue this quest, building ever more sensitive telescopes and running ever more detailed simulations, we are testing the limits of this narrative. We are not just learning about the universe's distant past, we are stress-testing our understanding of reality itself, probing for the cracks that might reveal even deeper truths. Let this journey inspire you. The next time you look up at the night sky, remember that you are not just looking at points of light, you are gazing at the grown-up children of quantum dice rolls, at a story that began in a fleeting instant of cosmic creativity. That story is still being written, and our questions are the pen. If you enjoyed this deep dive into the cosmos's beginnings, there are countless more mysteries waiting at the frontiers of space and science.